Welcome, class. This is Mr. Weiser. We're going to be introducing sampling distributions. This is a very fundamental concept for AP statistics. So you'll find this in Module 3, Lesson 4 of our packet, page 52 on that packet, and in the textbook, sections 7.1, AP Classroom, Unit 5.3 and 5.4. Our purpose of this class really is to take a sample of data and estimate whatever the population parameter is. So parameter is the value that we're trying to measure. So for example, if it's a mean, you might see this mu here, and we measure that with this x bar. So in your calculator, when we put some data in, we get an x bar, that's your sample mean. And that estimates the population mean. And you can do the same thing with sample proportions to estimate the population sample proportion or the population proportion. You'll notice that the sample proportion will have a little hat over it, whereas the population just has the p. And then we have our standard deviation symbol, the other third most common one, which is S of x if it's a sample. And then you might remember the sigma for the population standard deviation. And we always use our samples to estimate our parameters. We're never really going to be provided a parameter. So the purpose of this class is to come up with good samples so we can make good estimates of those parameters. In this first example, you're going to be asked to come up with what is the population, the parameter, the sample, and the statistic from the scenario. And in some of these cases, we're not really going to be provided a number, so we'll describe it in words. Let's look at example A together. Identify the population, the parameter, the sample, and the statistic in each of the following scenarios. A Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. What you'll first want to do is create a little chart. Population, sample, parameter, and statistic. For the population, what are we trying to estimate here? We're talking about U.S. adults. So all U.S. adults will be our population. Next, the sample. What are we sampling? We asked 515 U.S. adults if they believe in ghosts. So our sample was the 515 U.S. adults that were surveyed. What's the parameter we're trying to measure? Well, let's think about it. A yes or no situation would be some sort of percentage or proportion. So the parameter is P, the true proportion of all U.S. adults who believe in ghosts. And therefore, our statistic is going to be the sample proportion. And we'll usually denote that with a little hat on top. So that little P with a little symbol is your sample proportion. In this case, 160 out of 515 said yes, so 0.31. Pause the video and see if you can do part B. And we're going to go over it in 3, 2, 1. During the winter months, the temperatures outside the Starnes family cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes set the thermostat at 50 degrees Fahrenheit. She wants to know the low temperature or how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 10 randomly selected times. The minimum reading is 40 degrees Fahrenheit. So it looks like we're talking about the minimum in this case here. Let's see if we can identify our 4 things. So we're going to write our chart. And in this case here, we're talking about measuring the temperature, but we're measuring it at different times. So she sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 10 randomly chosen times during the day. So this part's important. And so our population is going to be dealing with the times, all times in a given day in this case. Therefore, our sample is going to be the 10 randomly selected times. Now, what are we measuring here? Well, in this case, we're talking about the minimum. The minimum. So our parameter is the true minimum temperature in the cabin that day. Therefore, our statistic is going to be whatever the sample minimum was. And so the sample minimum temperature in this case was 40 degrees Fahrenheit. That'll be our statistic. We don't have a symbol for minimum that we do for mean, so it's not really something that we have to draw out in this case. Now we could talk about sampling variability. Anytime you take a random sample, it's not going to be guaranteed to have the same exact distribution as another random sample. So for instance, if you have a bag of Skittles and you take a large bag of Skittles, and you take 20 of those Skittles out, is your color breakdown going to be the same as another 20 randomly sampled? Likely not. And that's what is sampling variability in a nutshell. So we're going to create what's called a sampling distribution, basically putting all of our possible samples together in a plot to make some sort of inference out of it. So for example, and we'll do this in class, but you may be asked to simulate what percentage of pennies have a shield on the back. You'll notice a lot of newer pennies might have a shield on the back, whereas maybe some older pennies might have the traditional Lincoln Memorial on the back. And the question might say, what proportion of them have a shield on the back? And we can do a sample of 5 pennies or a sample of 10 pennies or 20 or whatever, and combine all those samples to create what's called a sampling distribution. And we can do that with the years too. We can measure the years, maybe 2014 or 1992 or 2022. And we can average all of our years together in our samples and put them together in a distribution. That distribution might look something like this. So we might have something like a set of proportions. Notice that all these P's have a little hat. These are all your sample proportions. And look at all these X's. They have a little bar over those. Those are all your sample means for the years. And what would happen, do you think, if we were to basically make those proportions more and more and combine them onto one distribution? Well, let's explore that with a little simulation. So let's just estimate that the true proportion of pennies that have a shield on them is about 60%. So you might have a breakdown in your true population of 60-40. But if we do a sample of, let's say, 20, and we only plot one sample, that doesn't really give us a lot of information. In this case here, it looks like I have about 70% of those that have a shield on the back and 30 that don't. So what we can do is we can sample a ton of them at a time. So maybe if I put 100 samples on here, you might get something of a nice curve that might have one peak on it, and it might be centered around 60%. And if I keep adding samples to that, eventually it might have something like a normal distribution. And you can do the same thing with means. So if I say, let's say I have a sample of 20 and we have a mean of 10. So let's say the pennies are on average are a year of 10, since we can't really change this mean. And I select a bunch of different samples. Eventually those averages will look to be a plot on a distribution that looks approximately normal. And if you put that normal curve over it, it kind of fills in those gaps there. So sampling distributions, when plenty of those samples are plotted together, might create a distribution that we can familiarly do some calculations with. Let's back up into the real world for a second, because we can't theoretically do every single possible sample of all pennies. Let's do something that we can do. We have John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68. You are asked to list 6 possible simple random samples of size n equals 2 from this population of 4 sons. And we're going to calculate the mean height for each sample and display those samples in a sampling distribution on a dot plot. So the first thing we'll do is we'll get all of our different samples. So we might have 71, 75, 71 and 72, 71 and 68, and you'll see that there are 6 different samples. We'll want to average, in this case, all of these because we're asked to calculate the mean height for each sample. So we can add them together and divide by 2, and you'll get 6 different averages: 73, 71.5, 69.5, 73.5, 71.5, and 70. Now let's put those on a dot plot. What you'll notice on this dot plot is a nice symmetrical distribution. They're not always going to be symmetric, but in this case it is, centered around 71.5. I want you to think about that for a moment. Look at the original heights of these. See if you can think of a connection between this 71.5 and these 4 heights. Here's another example. To determine how much homework time students will get in class, Mrs. Lynn has a student select an SRS of 20 chips from a large bag. The number of red chips in the sample determines the number of minutes in class students get to work on homework. Mrs. Lynn claims that there are 200 chips in the bag and that 100 of them are red. When Jenna selected a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? So for part A, what is the evidence that less than half of the chips in the bag are red? Well, let's look at what we're provided with. She got 7 chips out of 20. Is that less than half of them? Yeah. So your evidence is simply, hey, 7 divided by 20 is only 0.35, not 25. So that's going to be less than 50%. So that's your evidence right there. Now let's provide two possible explanations for this evidence. Well, one, it's possible that 50% of the chips are red. Jenna just got less than half due to sampling variability. It's likely that she's not going to get 50% of those red, and it might be a bit above or a bit below. It's also possible that less than 50% of the chips are red. Mrs. Lin is not telling the truth. So both of those are possible explanations for this evidence, and we don't know which one's right. So what we want to do is we want to put together a bunch of samples. And so in this case here, we're going to have 100 simple random samples of size 20 from a population of 200 chips, 100 of them being red and 100 of them being blue. The dot plot here is going to show p hat, the sample proportion of red chips for each of the 100 simulated samples. And letter C, there is one dot plot on the graph at 0.80. Explain what this value represents. So in this case here, that 0.80 is going to be one simulated simple random sample of 20 chips. There were 16 red chips altogether. So the p hat is going to be 16 out of 20, which is 0.8. So in a sample of 20, 16 of them were red. Would it be surprising to get a sample of p hat equals 7 over 20 or smaller in a simple random sample of size 20 when the true proportion is 0.5? Justify your answer. So in this case here, if you look at all of the numbers that are 0.35 or less, I'm counting 15 dots here, so you can double check those counts. And there are 100 dots on this whole graph here. So we have 15 out of 100 that had a p hat, a sample proportion of values less than or equal to 0.35. Now, I would say that's not surprising because it's not a very small percentage. 15% is not really below our threshold of 5%. So we would say no in this case. So based on that previous answer, do we have convincing evidence that less than half of the chips in the large bag are red? Explain your reasoning. Well, this would be a no. It's not going to be surprising that that sample proportion is less than 3.5 by chance alone when the true proportion is 50%. So we don't have convincing evidence that less than half of the chips are red. Now, part F, suppose that Jenna's sample included only 5 red chips. Well, let's think about what 5 out of 20 is going to give you. Now that's going to be 25%. If you look on your graph here, we have 3 dots that are 25%. We don't have any that are less. So only 3 of those simulated samples out of 100 are less than or equal to 0.25. So that'd be a pretty surprising result to get a sample of 5 or smaller. That's 3% of those dots. So this would provide convincing evidence in this case that less than half of the chips are red. So to summarize, when you take a sample, first you're talking about starting from a population distribution. In this case here, our population is assumed to be 50% blue, 50% red in case of the chips. So you might have a bunch of simple random samples, and every sample is going to be a little bit different. But if you take every single possible sample, and could be a ton of these samples here, so they're not all listed out here, but these are all individual samples. You could put them together in a sampling distribution. And that sampling distribution, as we're going to learn in a later lesson, is going to be approximately normal, and we can make normal calculations with that. So the first step is to assume the claim is true. Assume that what is being told is true. Get a bunch of simulated samples, and then plot them in a sampling distribution to make some calculations. Here's a check your understanding. Pause the video and try this on your own. We're going to go over it in 3, 2, 1. Mars Incorporated says the mix of colors in its M&M's milk chocolate candies from its Hackettstown, New Jersey factory is 25% blue, 25% orange, 12.5% green, 12.5% yellow, 12.5% red, and 12.5% brown. Assume that the company's claim is true and that you will calculate p hat equals the proportion of orange M&Ms in a random sample of 50 M&Ms. What we want to do is identify the population, parameter, sample, and statistic in this setting. So if you're ready, the population is going to be all M&Ms from this factory. The sample is going to be the 50 that were randomly selected from this factory. The parameter, we're talking about the true proportion of orange M&Ms. Look at this. P hat is the proportion of orange M&Ms in a random sample of 50 M&Ms. So we're trying to calculate the true proportion of orange M&Ms. That's P without the hat. Then the statistic will be P hat, which is the sample proportion of orange M&Ms. Now we were told that the proportion of orange M&Ms is 25%. So that P is claimed to be 25% here. We don't have a sample yet, so our statistic is unknown, but we'll still say P hat, the sample proportion of orange M&Ms. Let's graph the population distribution. I use technology to help with this, but 25% will be your two biggest graphs for the blue and orange, whereas the green, yellow, red, and brown are all 12.5%, so they'll peak out flat at 12.5%, and these are your percentages, so your relative frequencies. Part C, imagine taking a random sample of 50 M&Ms, milk chocolate candies. Make a graph showing the possible distribution of the sample data. Give the value of the statistic for the sample. Well, we're going to use due to sampling variability, we can have really an unlimited amount of these. But if we talk about samples of size 50, I'm going to put 50 in there. And there's one possible sample. And I could do it again. I could do another sample. There's another sample. And we could keep going. And theoretically, those could change all in all. But if we were to eventually combine them together, you might get something that resembles our distribution. Now, in this case here, I have one that's already done. So here's one that could potentially be done. You might have a sample that it looks like this, but we're asked to give the value of the statistic in the sample. Remember, we're talking about orange candies here. So in our scenario here, the sample proportion that we're trying to come up with, that statistic, in my sample is going to be 10 and there's 50 of them. So my P hat is going to be 10 orange candies out of 50. So my sample proportion is going to be 0.20. Your answer would vary on that. Part C or part D, which of these three graphs could be approximate sampling distribution of the statistic? Well, let's think about this for a second here. That first one is just a random breakdown of the colors. That's not a sampling distribution because you notice it's not talking about percentages here. It's not talking about proportions. It's talking about the frequency of the colors, blue, brown, green, orange, red, or yellow. So that first one's not really going to work here. The second one, if you plot where the center is, about 25%, remember we're told that 25% of those M&Ms are orange. So assuming that claim is true, this one looks to be centered around 25%. So that's a pretty good estimate of maybe what the sampling distribution would look like. Now that third one, that's a little bit off. Notice that that's centered maybe around 12.5% or 13%, somewhere around there. And so that's less than that 25%. So I would say the middle graph is going to be the one that would be the best approximate sampling distribution of the orange proportion. Now, when we're talking about sampling distributions, it's really important that we can make sure we can have an unbiased estimator. Unbiased means that we are trying to make predictions that represent the actual parameter in question. So for instance, let's go back to this example that we did earlier with the heights. If you look at your four heights that were over here, 71, 75, 72, and 68, the mean of those heights, add them together and divide by 4, you're going to end up getting 71.5. Now, if you take all of these dots and get the average of these sample means for the samples of size 2, you're also going to get a mean, so that little mean of all the individual means of 71.5 inches as well. Notice that those are exactly the same. So this would be an unbiased estimator. In other words, the average of all of these little sample means gives you what we're looking for for our population parameter. So that is an unbiased estimator. Not all estimators are going to be unbiased. Take a look at this one. The graph below represents the sampling distribution of the sample range of those heights from size n equals 2 from the population of the four suns. So remember, we have four different uh, heights, and we can get all the different ranges based off of samples of size 2. So is the sample range an unbiased estimator of the population range? Well, let's take a look at the sample range, the mean of the sample range. We got all these different ranges. We got 1, 3, 3, 4, 4, and 7. If we take the average of all those and compare it to the actual range, we'll have 1 plus 3 plus 3 plus 4 plus 4 plus 7, and there are 6 of these. So that's going to give you an average of 3.67. Now let's look at the actual range, okay? The highest minus the lowest. 75 and 68. Now, 75 minus 68 is going to be 7. 7 is way up here. Does this estimate, with accuracy, the actual range of the population? Well, the answer in this case is no, okay? Because the average of these sample ranges is not equal to the population range, we would say this is not an unbiased estimator. In fact, it is biased. So we would not want to use the range as an estimator of we would not want to use the all the ranges of all the samples as an estimator of the population range. So that's a big no on that one. Now, when you increase your sample size, what's going to happen to your variability in this case? So if I were to plot all of my pennies and I had size 5 and I got my average age, you'll see that in this case here, it's more spread out. But if I take a sample of size 20, notice it's going to be less spread out. And if I take even smaller sample, it's going to be less spread out than that. I'll show you a less concrete example here. So we'll start with a sample of size 5. And if I take a bunch of samples, let me say, 1,000 samples here. This might be a distribution with a sample of size 5. Now, if I make that sample size higher, so we'll say 10, notice it got to be skinnier. And if I make that sample size, we'll say 50, it got even skinnier. So the higher your sample size is, the more precise it's going to be, the more it's going to truly estimate what the true parameter is in this case here. So it's going to be more precise, less spread out in this case. So that distribution will be less spread out. And the moral of this is if you increase the sample size, you're going to have a smaller standard deviation. So it's going to be less spread out. It's going to be more precise in your predictions. So let's look at example 4. For quality control purposes, supervisors at a battery factory regularly select random samples of batteries to estimate the mean lifetime of the batteries they produce. Here is a simulated sampling distribution of X bar, the sample mean lifetime, in hours for 1,000 random samples of size n equals 100 from a population of AAA batteries. Notice that this sampling distribution seems to have a nice normal shape or very close to it. Now, what would happen to this sampling distribution of the sample mean if the sample size were 50 instead? So remember, we're starting with 100. But what if I only took 50 instead of 100? What's going to happen to this distribution? It's going to be more spread out. It'll be more variable because the sample size is smaller. So you might see it look something like this, where it might be flatter and more wide at the edges. How will this change the sample size affect the estimate? Well, because there's more variability, your estimate's going to be less precise. So to summarize that in terms of like darts, you could have a very precise shot, but if you're going to have a biased type of way to get that shot, you might always be hitting that dartboard at the wrong spot. So you could be very accurate, but wrong. Now, you might average your darts right in the middle, but you might have more variability in those averages. So this would be an unbiased estimator, but it would be a little less precise. You might just be off in both categories. So you might be more variable, but also unbiased or biased in this case. And if you have a very precise and unbiased estimator, you're always going to hit that bullseye. So this is really kind of the goal here. This is the sweet spot. Not going to hit that all the time, but that's the idea. Here's a check your understanding to finish this off, and then we'll be done with the video. The histogram on the left shows the wait time in minutes between eruptions of the Old Faithful geyser for all 263 recorded eruptions during a particular month. For this population, the median is 83 minutes. We use technology to select 500 simple random samples of size 15 from the population. The 500 values of the sample median are displayed in the histogram on the right. The mean of these 500 values is 80.5. So on the right, we'll have a bunch of sample medians, 500 of them. And then on the left side, we have all 263 recorded eruptions. Part A, does the simulation provide evidence that the sample median is a biased estimator of the population median? Justify your answer. We actually don't need the graphs for this. If you look at the numbers, the mean of these 500 values of the sample median on the histogram at the right is 80.5, whereas the median for the population is 83. So because the question says, does the simulation provide evidence that the sample median is a biased estimator because the mean of the sampling distribution of the median is not the same as the population median, I would say yes. All right. Remember, a unbiased estimator is going to give you the mean of your sampling distribution to be exactly the same or very, very, very close to the same as what the actual parameter we're trying to measure from the population is. Since we're trying to measure the population median, or since we're trying to see if this sampling distribution is unbiased, take the average of all of these medians. If it's not the same as the true median, it is a biased estimator. So we have evidence it's biased. Suppose we had selected samples of size 30 instead of 15. Will the variability of the sampling distribution be larger, smaller, or about the same? Explain your answer. Well, you might recall that when you have more increased sample sizes, your variability is going to decrease. So larger samples are going to provide more precise estimates because larger samples include more information about the population distribution. So that variability is going to decrease. And that's it. Thank you for watching.